Make them fun.
Okay, keep the hands raised, please, for the empty spots. So you can find easily. Guys, everyone that has empty spots, please their hand raised. Identify about that. Thank you.
Yeah. Yeah. What? Oh, like English or Spanish? No. I haven't taken anything. I was going to study abroad, so I should use that one.
Don't go into Spanish. That English class.
Hello? Can everyone hear me in the back? Okay, cool. Hi, welcome to our board workshop. It's being run by both Emma and Purdue and Purdue classes. So welcome. Just a raise of hands, how many of you are okay, cool. What about Emma and Purdue? Anyone from both? Okay, cool. So hi, my name is Ananya. I'm the VP of Operations of Emma at Purdue, and today I'll be talking about basics and conceptual side of embeddings.
Okay, awesome. So, hello everyone. My name is Sunan. I am going to be talking about the programming aspects, so going from understanding what the concept is to actually getting or obtaining word embeddings.
Alright, I'm Mikhail. I'm from Purdue Hackers, and I'm going to be talking about some applications for embeddings and doing them on your own data set.
So if you haven't already, sign in from the QR code here. So before we start, I just wanted to talk about some upcoming workshops that we have. This is actually going to be part of a 3-part workshop. The second one is going to be on 5th of October, where you will be making a chatbot using sentence embeddings and that. Then the week after that is going to be one on fine-tuning LLMs. Currently, the time and location for both is to be decided, so please join our Discord servers for the lead up there for the I don't see any phones out yet. So for getting ready for the workshop, can you guys please go to the laptops and then navigate to the notebook.ify, then go to Open Collab, File, and make a
Guys, also one more thing. When you start the runtime environment, convert the runtime environment from Purdue environment to a GPU environment, because that way things will just train a lot faster. My bad, I forgot. But yeah, thank you. What? Oh, when you set it up, just
have a thumbs up from people who are on the. I'll give you guys some. And the link up here is also in both of the papers, so you guys back in your. And I see the is there anyone who's not registered?
Did you say change the runtime type to GPU?
Jimmy's gonna go over that when he starts the
Okay.
part. Or not. Any helps?
This Wi-Fi is
Oh,
slow.
wow. Technically, you don't need this for my side.
Yeah,
So the walk. So as we said, in this workshop, we will be learning about word embedding, training our own, and then them for some applications. Before, I just wanted to have a quick section on the basic vectors. I have a really good anyone who has this? Okay, so this will be a super quick overview. There's some things that are relevant to our workshop that I'm going to talk about. So a vector, as you already know, is an ordered collection of numbers that can represent data and the computer science perspective. Each number in the vector is its element or component. As you know, it could be visualized through. For example, if we wanted to do analytics on house prices, the only features that we cared about were the square footage and price, we might model each house with a pair of numbers. It can also be seen as a 2D vector, where the first element indicates square footage and the second one price. And note that the order matters. And as you might have guessed, or as you already know, possibly, vectors can have many more dimensions. And it can be difficult to visualize vectors that are in higher space, but you know that they. And any n-dimensional vector can be specified as d1 where those. Another thing to understand about vectors are the operations. Ones I've included in this are the ones that are relevant to embeddings. Two of them, the very simple ones, are vector addition and subtraction, and then there's also simple. So for vector addition, the way you add two vectors is element-wise sum of components. For example, adding 1, 3, 2, and 0 gives us 2, and then subtraction is the same thing, but instead we take. So if we take the same two vectors but subtract them, that gives us 2, negative 6, 2. And of course, the dimensions of the two vectors that you're adding, subtracting, must match. So for cosine similarity, it's basically a measure of similarity vector and takes values in the interval -1, 1, where a value of 1 indicates the same vector, 0 indicates vectors, and -1 indicates strongly the same. And the value between -1 to 1 basically how similar the direction of the both vectors in are. So I have this visualization. So one quick thing, The green line is basically the value of the cosine red vectors. So as it's running now, you can see that when both of the vectors point in the same direction, the polarity is 1. When they're perpendicular, it's 0, and then when they're in opposite directions. And then I also included a link here if you want to know how it's exactly, but it's not necessary for this. Okay, now that you have the necessary background or review about vectors, let's talk about a useful application of them in our word embeddings. Machines work with numbers, you know that, and it's pretty straightforward to think about how we can represent numerical data vectors for machine learning models. But what about non-numerical text data from the application? Since we just talked about vectors, vectors would be a good guess. So let's take a look at how we could use them to non-numerical. The embeddings in machine are dense representations of real-world objects, and these are expressed as a vector. What dense basically means is that the vector, most of the values of the vector are non-zero. If they were mostly 0, then it would be a sparse vector. So word embeddings then are just embeddings, but for words, and they represent words as continuous value vectors and multi-dimensional. And if you're thinking about it, you could see how there could be infinitely many choices of what vector you could use to represent. Because the vector can have any dimension you want, 3D, 500 dimensional, 1000 dimensional. And each component can theoretically take values between negative and 50. So how do we know what are good vector representations are? That takes us to our next section, the basic characteristics of good word. First one is that word embedding should capture semantics. Semantic basically means like the meaning of, and this means that words that have similar meanings but that are used in similar contexts should have vectors closer together. And closer together is basically by the cosine vectors by about it. So in this illustration below, instead of using numbers, it's coded like the embeddings are coded with colors, and red and blue are like on the opposite sides of the spectrum, with the white being in the middle. And you can see that the embeddings for man and woman are much more similar to each other than either of them are to kids. This is kind of a feature that we would like in word embeddings. And here's another more exhaustive list of examples. So as you can see that there's a straight red column through all of the words. This kind of indicates that they're similar along that dimension. You can also see that woman and girl and boy and man are similar to each other in a lot of places. Another thing you might have noticed is that girl and boy are also similar to each other in some places where they're different from man and woman. So like one interpretation of that could be the concept of. And then another thing is that all but the last word, water, has this blue along this dimension. And this could possibly be because all the other words represent water is just an object. And then finally, if you look at the embeddings for king and queen, they're similar to each other in some cases where they're different from others, and that could encode the idea of the word. Another thing, and this is my favorite part of embeddings, is that they can usually solve analogical tasks. So if you think of the formula king minus man plus woman, the thing that we would think of would be clean. So if we do that with word embeddings, you would see, assuming they're good word embeddings, the embedding after subtracting man and adding woman would be more similar to clean. And ideally, from all the words in our collection of word embeddings, we should have embedding closest. And then finally, good word embeddings generalize well to unseen data. And we want this because if they're very specific, then they might not be useful in various applications. The fourth point is kind of like an extension of that. So if there was a word that we trained our embeddings on that wasn't present, then we would not have a representation for that. So we would ideally like to do that in some techniques are using subword embeddings or a generic unknown. So another thing to note is that word embeddings can also be used to represent functions. The most straightforward way that you probably think of is just having a vector. For example, if the word embeddings for the words I like and vector are the following, in the sentence I like vectors, represent that of the. But as you might have noticed, if you do this, then sentences of different lengths would have various sizes. So another simple way to do this is by just averaging the embeddings along each sentence. For the same embeddings that we just talked about, sentence I like vectors represent as 1 through 2, and as you can see, that has the same difference as each. And clearly, this might not be the best way to represent a sentence. Just know that sentence embeddings do exist, and that would be a focus of the second workshop. And now that you guys know conceptually of how we can represent words, sentences, and what good words look like,
Okay. I should be audible. Can someone please confirm to me that? Okay, amazing. So before we start talking about how we can practically set up word embeddings, if you have any questions about word embeddings, or are we, if you just say something. Yes, no, maybe. Okay, good. So I would take that as a yes. Generally, okay. So before we get started with that, I'll also just quickly run you through setting up the runtime type. So in your Colab notebook, all you have to do is go through the drop-down menu and select that option and switch it to the GPU. Don't switch it to the CPU. We are currently with the code only running on CUDA right now. So yeah, once you do that, it will restart your runtime, and you should be good to go. So yeah, the entire part of the programming is covered through this entire Colab notebook. But for ease of use, I'll be using this window. So just let me know everything. And this is for a little bit of visual description. So let me make sure that this looks fine. So okay, fantastic. Everything seems nominal. Now, the way that we would approach or practically approach setting up a vector is by creating an autoencoder network. All right, and what this autoencoder neural network entails is, if I can open pen correctly, you have this input layer, okay, and this input layer is a vector embedding, but a very bad one, right? This is something that you come up with manually, and it's not fantastic. We send this through a hidden layer, and this hidden layer generally is smaller than the size of the input layer. In our case, since we're going to be using a toy example, so that things train in real time and we're not waiting here till tomorrow morning, it would probably be reversed where the hidden layer size would be larger, but that's okay. From there, we get a output layer, and this output layer is not super relevant to us as far as the weights are concerned, but it is super important to get the weights that we want in the first. And if that sounds confusing, that's okay. We'll talk about it in a second. So the way a neural network works is that it is feed-forward in nature. So you have your input layer over here, you have your hidden layer over here, and you have this output layer. Okay, and it goes from left to right. It processes, and this output is your final result. You get a set of weights that allow you to sort of make the connection from this input layer to the hidden. right? We have this data set that we are trying to or going to train on today. So it's corpus CSV. On the Colab notebook, if you run this cell and then you open your file structure, you will be able to see this directory, and within that data, within that you will be able to find this this corpus.csv and the diplomacy.csv. So we'll get to diplomacy.csv, but for now we have corpus.csv that's important. So that, and all of our source code is structured as a Python package, which we'll get to in a second. Okay, so we have this machine learning or neural network that we have set up. Okay, what we really want to obtain is this set of weights over here, right? This intermediary over here that makes the input layer the hidden layer, and this set of weights is our actual embedding. So this is our embedding or what we want to get. And now is where we start talking about how do we actually set up this the data part of it, right? So if you guys have taken or watched a video about machine learning, a lot of people will tell you that data processing is like 80% of machine learning. They're right, unfortunately. So let's talk about the data processing. So one interesting part of word2vec or vectorizing a word is that you don't need a bespoke set of target data. It is self-supervised. So I can take any body of text that I like and not have to do any more pre-processing over it in order to get the final embedding. So that is good. So for an example, right, I am going to use the sentence "I am happy." Right, this is the sentence that I want to get a vector out of. So there are a couple of things that I look at. The first one is my vocabulary, right? What words are present in this? So in this sentence, we have 3 words present, and we want to convert these 3 words from from this string into something that something numerical, something that a machine learning model can understand. Because machine learning models do not actually interpret words; they only interpret numbers. So we have these 3 words, and in order to convert these 3 words into a vector, we use the strategy of one-hot encoding. So how many people here are familiar with one-hot encoding? Can I get a raise of hands? Okay, I see a couple. It's not super complicated. We'll get it in a second. So in order to create a one-hot encoding, my first step is to set up this a array or a vector with 3 zeros. So 1, 2, and 3. These 3 zeros actually correspond to the vocabulary. So I have 3 words: I am happy, and I assign each of these indices 1 word. So this word becomes I, or this index becomes I, this index becomes am, and this index becomes happy, right? So this is our encoding, so to speak. Now, if I were to encode one specific word like I would assign a 1 to the index that I have set I for earlier, and zeros for everything else. So this would be the word embedding for I. If I were to set a word embedding for am, I would do it by setting the am index to 1 and just zeros. This is one hot encode. Does anyone want to tell me what would the encoding for happy be, or should I do it?
001.
001, exactly, perfect. So I'm going to do that, just leave it as H, and that's the encoding plan. So this is how we will encode all of the words that are present in our input, right? So this will go all the way over here. Now, let me zoom out a little bit so that everything is in context. Okay, this is our input layer. Okay, the hidden layer is cool because we don't have to worry about what that should be. Now let's worry about the other thing, and that's the output layer. So I'm going to go over to the next page over here and start talking about what the output layer is. There are 2 ways of setting up the outputs or the targets. This is the output that we want our machine learning model to predict. We want parameters such that it is able to obtain this array or this embedding that we have set. So one way of doing this is a continuous bag of words, or CBAG. There is also skipgram, but we will cover that for the sake of time. If you are interested in it, the code is included inside the repository. So we will talk about SIVA. The way SIVA works is you identify all of the words that are present in the vicinity of the input, and you get your model to predict the actual word itself. So I misspoke over here when I said this is the input. This is actually the output. This is, and we have to figure out the input. So I apologize for that. So our prediction target now is our is the one-hot encoding of the words inside our sentence. And to figure out the input layer, the way we go about that is we take all of the words that are present in the vicinity and set all of those vector indices to 1. So for instance, in the I am happy sentence, in order to encode am, I would encode the I as well as the happy to 1. So the vector for am, the input vector for am becomes 1, 0, 1, and the vector embedding for I becomes 0, 1, and then again 0. This is because am is the only word that is present adjacent to I, right? And we do this entire process for all of our input data in order to create a sample data set. And the code for that is present over here. Again, we will not go into too much detail when we talk about it. Couple of things to note is I make all of the words lowercase in order to just keep the vocabulary size as small as possible and make sure that we have a lot of dataset samples. This pre-processing, don't worry too much about. It's basically just doing everything that we have on this right window over here. The length and the get item is for actually obtaining the index. So I can give, suppose I have say 2 of these, right? This becomes the dataset entry 0 and this becomes dataset entry 1. So I just do dataset like in the code, oh my god, dataset, and then just give it as though it is an array and it will give me this over here. Okay, right. Does this make sense? Or how have you just been done? Make sense? Good. Nice. That's our autoencoder model started, and in order to actually figure out the loss function, we're going to be using cross entropy, and the atoms are, I think STDs are optimized, but it's not super important. Don't worry too much about it. These are just details that are metadata. So now, again, to reiterate our goal, it's not to train a model that has the biggest loss function, or I guess it is, but we don't want the model in its entirety. We just want the weights that are present in this layer because these are our actual vector embeddings. So now I'm going to quickly talk. This is the architecture. This is exactly as we described over here. This is the code version of it. I have a couple of linear layers and softmax. Softmax is an activation function that converts a ratio or a numeric ratio into probability. So it basically makes it such that if you add all of the values that are present inside this output layer, it will sum up to 1. So that is important in order to train our final model. Then this is the forward pass that just discusses this entire process, and the embedding property allows us to actually get the weights that we weights from the first linear layer. So if I run from the source directory, I can run source, not source, in source, word to vec, and then architecture. It will print out the actual model for me, and if I give it a sample input, this is the output that we get. So if I want the embeddings from this model, I can just do embedding like so, and these are the weights that we're trying to get. So fantastic, I guess, in the sense that we got a series of numbers. However, it's important to note that these numbers are random. Okay, so they mean nothing to us. We can give these series of numbers to a model and say this is our input embedding, and it would be awful. Okay, the behavior the emergent behavior that we saw with the king minus man plus woman equals queen is not going to happen if we just have random bits. So we need to actually train it. So this is our actual model with the embeddings, which is fantastic. But let's actually do the training. The training loop is as follows. It is a straightforward training loop, and all of the details were exactly as we discussed earlier. So do not again worry too much about it. So I have W2V over here, and I just run train. It is going to train for 1,000 epochs, and you can see that the loss function it's kind of going down over the 1,000 epochs. It went from 4.6 to 4.2. Now it is important to note that this is not inherently fantastic, and that is because our data set size on our corpus is so small. We only have how many sentences? 7 sentences, if I can do math correctly, and out of these we get, I think, 33. So this is not a lot of data, which is why our error is particularly high. In any case, this is our embedding function, and if you want to get the actual embeddings, this is our trained embedding, so it will work significantly better than the original random set of weights. So now, in order to actually get this sort of embedding refers to the embedding for the entire vocabulary, right? So we have 33 words, which is why also we have 30 samples, and these 33 words are each represented in their own vector. If you want to get the vector for it, there is one straightforward thing that we can do. So first, let me just check if we have the words that are present. Where is my code? Oh yeah, data set. Okay, so I get my words over here. So remember when we mentioned we create a vector that refers to or that creates this sort of map where I refers to index 0, am refers to index 1, and happy refers to 2. This is basically what that is. This is that index. So OSX refers to index 0, is refers to index 1, and so on and so forth. So that is our dataset words. And if I were to get, say, for instance, model.embedding, and then get all of the 784 vectors or the 784 indices inside the specific vector for the index of the original word, this will give me a vector of 784 numbers, and this is our final trained embedding. So this is your trained embedding that actually, and that is fantastic. So it is important to note a couple of things. First, this is a toy example, right? What I mean by a toy example is that it's super tiny. We have only a couple of input sentences, and as a result of that, the embeddings are not very good. We can sort of upgrade to a bigger data set, but another problem with that is the fact that the vocabulary explodes, right? So if I were to train this on the entirety of Wikipedia, the shape of the model will exceed the 33 size that we have. So it will be somewhere around 1 million in the input and another 1 million in the output. So that is a huge amount, and not something that we can practically see. So in order to fix that, what we do is we switch to a framework. We use abstraction in order to simplify the entire process for us. We don't have to worry about all of the training loop, the architecture, the data set. We just let the framework handle all of the heavy lifting. So in order to do that, there are a couple of things that we can look at. Okay, so under Jensen/train, there is this code over here, and this is the entire code that we need in order to train the word-to-vec model that we previously used in a much more optimized way. And the way that it does it is using some clever tricks with sampling to restrict the number of weights that we or the number of calculations that we perform. Which it just does not happen by default if I just that in part is because these vectors are very sparse, right? Earlier we mentioned we want to obtain dense vectors. Technically, this is an encoding of the model of our vocabulary. This is an embedding, so to speak. But it's just as bad as our random weights. simply because it does not encode any meaning. The computer finds these three completely separate words and does not identify any correlation between them. Anyways, that is the PyTorch part. Let's talk about Jensen. Jensen is a library that allows us to automate the word-to-vector process. So in order to actually train a model, all you really have to do is first install this prerequisite pump library and then actually load your dataset. So I have two datasets over here. There is also this diplomacy dataset. So I'm going to load pandas and pull this up very quickly. So columns, I have text over here. So these are a couple of samples that are present in our dataset. So I have 0 and this will give me 1 parameter, right? So this is one specific sample from which we will extract all of the text and train on. Like this, we have 184 conversations. To give you guys a little bit more of context, diplomacy is a game where people try to convince each other to not start the fictional equivalent of World War III. So that's what we want to create embeddings that fine tune on. And they will basically learn the vocabulary that we will teach. So now I'm going to actually start running the code. So I'll remove this process and start a new one with Jensen. And you will notice that the training process of this also is actually, wow. I need to change the dataset. So in order to actually change it from the corpus.csv to the diplomacy.csv, you will have to go into the const.py file and just change this to diplomacy and then run it. The reason that it gave this error was because man is not present inside this original text corpus that I discussed, right? So that is the reason that it's just not present. If I run this one more time, hopefully it's not going to give me issues. So packet is up to date and already right? Now, if you were to sort of check the model for a sample evaluation, what we can do is use model.wb and get most similar, and this will basically find the words that are the most similar ones to whatever we input. So if I search man over here, we see this is on this side. This is the set of words that the diplomacy dataset thinks makes the most sense. So man, matter, man, lol, man, kinda, man, these are the closest things that exist to the definition of the word man. As you folks would have guessed, that's not ideal. It is actually very, very bad. It's not helpful at all to us, right? So the way to get around this sort of issue, or also something interesting, right? Before we sort of get to that, I also want to show you guys one funny thing. So you can calculate the previous correlation that Ananya had spoken about, where you do the king minus man plus woman, and it should give you something that it says that queen is the closest. So then let's just try and see how well that works, right? We'll do king minus a model dot word vector of man. It says plus, I noticed in the code, and that's my bad. And that's okay. So I will run this code, and it will give me the word woman not present. So it's a gaming data set, and the vocabulary is key. So it is one major error or one major flaw that you will find in a lot of data sets that even you work on. A lot of times you will find a risk of bias within your data, and you have to be especially careful to ensure that it doesn't exist, because otherwise you have a much bigger problem on your hand, and you should definitely not deploy a model to production. So that is something that is important to keep in mind. Now that we have established that we do not have good data, let us use Google's resources that does in fact have good data. So in order to use a pre-trained model, you could go to the models directory within the repository and see we have this Google News /vector -300.basic.gz. In any case, this is a series of weights that is very huge and is trained on a huge corpus of data similar to that of Wikipedia. Now, because this data is so extensive, it works a lot better than before. And before I sort of labor that point, I'm going to start actually running this code because it takes a significant amount of time to load everything up, just by the nature of the size of this. I think it's 1.5 gigabytes of course massive. Anyways, as we wait for this to load, we can talk more about good data and just make sure that your data is sorted. Actually, I don't have a lot more to say about that. One interesting thing about the code, by the way, is that in our previous model we used word to vec, and while the actual code is the same, the feedback is for loading the pre-trained model, and the APIs for them are slightly different for some reason. So you originally used to be model.moseSimilar, and this was basically perfect, and Gensim then deprecated this. So now it's model.wv for word vector and then .moseSimilar. But since this is an older set of weights, we don't need to do that, and we can just use model.moseSimilar. So now that we have a model that is hopefully more capable, let us try to perform similarity search for the word man. And this is good. We have a couple of or a set of vectors that make a little bit more sense. I would probably rank men a lot above women when we talk about more similar to man, but that's okay. So this is a somewhat better model, but if we want to talk about stuff that is actually more resilient, like for instance, one issue that you cannot get around for word vectors is the fact that every single word, regardless of definition, or every single word with the same set of characters, regardless of definition, means the same. So a reward bank and a financial bank, those two words, or the word bank has to have a single representation and cannot have different representations for different entities. And that creates a fundamental problem within the actual data set. So we'll talk about sentence vectors in our next part of the workshop that actually gets over this challenge to a certain extent. So finally, before I wrap, I want to try running the most similar thing with the correlation that we or the emergent behavior that we discussed. So I will take the king and I will remove man and I will add a woman and I will run this. And although the closest thing is king, we do see that the next closest thing or the next closest vector that we do identify is queen. So there is some emergent behavior over here, which is very, very cool. So that is what I have to cover. Now Mikhail will take over for the hacking part of this work.
Microphone actually works.
I
Okay. Better now?
now, right?
Okay. Yeah, it sounds good. Okay, so now we're going to talk about
Oh, slides.
yeah, okay. So now we're going to talk about training word2vec on your own input data set, right? So finding a good data set can be kind of difficult, but there's two pretty interesting ways to get one. One of them is ConvoKit, and this is a library that has a data set for each subreddit from So using this, we can get, for example, two subreddits. This is another Chrome plugin that you can use to download as a CSV. So you can find your whole group chat and figure out song with your friends. All right. So in the collab, we already have this code to grab. Um, um, I'll just write it in.
Hey, do you-
Alright, there should be a header for the hacking section somewhere in the collab, and that code is going to load the Purdue subreddit and create a CSV file in your collab that has like a bunch of Purdue messages subreddit. So hopefully that's here. Alright, anyway, what I was getting to is that it needs some changes anyway. So I'm just gonna type it out here. So first, what we want to do is pip install complicate. And remember, this is the library we talked about that has like a bunch of data sets. So not only does it have like every subreddit, it has a ton of other things that you can find in the documentation that look on the slides. And so this is just yeah. So this is just using the library, and I just found this on the documentation. And then we are grabbing the Purdue subreddit corpus. And we're opening this file. So this is going to go in the data subdirectory where we already have some input purposes. And you can name this whatever you want. And then one thing about the Purdue the data is that we're going to have to filter it a bit, right? So the input format to the model where CSV is a comma separated file. So we have to get rid of all the commas, otherwise it puts it in arbitrary ways that our parser can't deal with. So what I'm doing here is I'm just replacing all of the commas, the text with nothing. And I'm also going to make everything lowercase. And what this does is it just ensures that things are more like normalized. Because otherwise, when people talk about uppercase, lowercase, they're going to go into the corpus or into the model as a different word. And because our data set is actually like a little bit smaller than we would like, so we really want to make sure that we have like as much occurrences of each word as possible. And now since the corpus actually just comes with a list of comments, what we're going to do is join all of those into the C. And one last thing is that our input corpus from this library is potentially really large. So Purdue is like a fairly small subreddit, right? But even with the Purdue subreddit, I was taking like a couple minutes, like as in like 10 minutes to train on it. So what I'm doing is I'm just taking the first 100,000 or so comments, and this is like kind of borderline. I saw that with less, it was like doing really badly. So if you have more time to play with it, then I would encourage you to put it higher, but it will take like a while to train. And so now what we're doing is we are putting this in the file. And before we run this, I just want to say, like, don't force yourself to run it on Purdue. I'm running it on Purdue for demonstration. You should run it on like wherever you feel. And this will take probably a few minutes. Okay. I forgot a really important function, which is open. Okay. So that's this is the process. It looks like it unfolds. Alright, I'm just gonna break the recording and plug it into my laptop. Yes, but if the yeah, but if the repo is gone, it's still like not gonna work. So I'm just gonna plug it into my laptop. Alright, in case a few of you are ahead, I'm just gonna tell you verbally yeah, no, my laptop is like it's oh. Okay, so we already loaded this data set before, and it got the data set to load from this file that's called const.py. So on the left, if you click the folder button, not here. If you click the folder button, you'll see the whole directory, and there will be this folder called Word Embeddings Workshop. Under Word Embeddings Workshop, there will be source, which is src, and then const.py. So, okay, there it is, finally. Yeah, so const.py will show up on the right. Double click it over here. And here you can see that you have this dataset path and this column name. So you're going to want to change dataset path to Purdue.csv or whatever you name that file. And then you need to change the column name to header. And that's just because of the code that I wrote earlier. Yeah, so now once you run that, whatever you run this cell here under Gensen custom word detect, this CSV is going to read the proper CSV. And you might want to run this code first. This might not be in the notebook. I'm not sure if it's updated. But you should be good about it. So once you rerun this, right, you'll have reloaded the data frame. And here we can see that here's some Purdue data. And I've actually already trained it. Yeah, so I've already run all of this. For you, if you try to run it, it will probably take a minute, depending on how much data you took. And now I can see some things, right? So there's some like data specific to Purdue that no other subreddit is going to know, right? For example, if I put in 180, can anyone guess what shows up?
Yes.
Yes, okay, it's not quite CS, but it's like every other CS class. I was actually hoping to get something more inflammatory, so I searched like 252. They're like classes that no one likes. Unfortunately, it just shows other classes. If I put boiler, clearly Purdue likes boilers. Yeah. Yeah, Tracer was uninteresting to be honest. You can get a list of all the professors, I guess. Or, I don't know. Yes, you get all the majors. Yeah, so there's some interesting things we can do. You can see that, yeah, you can see that it's still like not great at this example. Oh, this is fun. So we got a regex, I guess. Yeah, but depending on the data set you try, you might get some really interesting results. So,
Curious, what's most similar to nothing? Sorry.
the fancy string?
Yeah, I'm curious what it would do.
Yeah, because I guess when we process the data set,
That's fair enough. That's just
it's yeah, I was looking for rain. There's yeah, I was actually like really expecting to see that IU sucks. But yeah, we just got like a list of other schools.
What about
Nature? Yeah, I guess it's a list of all the coaches. No, that is a, I didn't. Yeah, so if you find any interesting data sets, then send it to the survey around the time.